Okay, so hello. My name is Louis. I work for Amazon. I'm also involved in the C++ standards committee, and I'm involved in a Boost community as well. I'm the author of Boost HANA, which is like a crazy template metaprogramming library. And so you will notice that I have like a tendency to push the language, into its dark corners during that presentation. What I really enjoy is actually pushing the language to see, where, like, what kind of stuff we can do in the library, and where we need to stop because the library just can't do it anymore. So today's topic is runtime polymorphism, right? I think it's a really, really important topic, and it's something that we are only starting to kind of, explore in C++ right now, because we've taken something for granted ever since C++ was created, which is inheritance. So we're going to see kind of alternatives to that today. And also a quick disclaimer. I'm usually quite good at jet lag, but not this time. So if I'm mumbling and it doesn't make sense, I'll just ask a question and clarify. Okay. So first off, when do you need runtime polymorphism, right? So imagine you have a bunch of classes, and they're all related by their interface, okay? They all have something in common. And say you want to return any one of these types from a function. And the important part here is that it's which type we're going to return depends on something that's known only at runtime. That's really the important part here. So based on some user input or something like that, we want to return one of three types in this case. So we need to somehow get a single type that we can return from the function, but that type must be able to represent any one of these three concrete implementations. So in that case, we need what's called runtime polymorphism. Or maybe we have a set of types, and we want to store any one of these types in a container, for example. So we need to pin down one type, say this is going to be the representation that's going to be stored in the container, and then actually put multiple different implementations in there. So sometimes variant actually works, and it's enough. But one important thing to note with variant is that it only works when you have a fixed set of types that you know at compile time in advance. You have to be able to basically enumerate, name those types as a programmer when you're writing the program. You have to say it's either that, or that, or that, or that, and that's it, and nothing else, right? And also you have to use visitation, which might not always be the most convenient thing to do, but it's kind of it's not such a big deal. The real big deal is that you have to be able to enumerate your types in advance, which is a big, big, big restriction. Because imagine you have a library with an API that accepts any vehicle, for example, okay? And you don't know what vehicles you're going to get up front because your users might decide to create a new type of vehicle. So you can't possibly take a variant in your API then. So you need runtime polymorphism whenever you need to manipulate an open set of types that have some relationship to each other. If they don't have a relationship to each other, then you don't really have polymorphism. You just have different things. But if they all share some interface, then that's when you actually need runtime polymorphism. Of course, if their representation is all the same, it's also not such a big challenge. But when they're represented, like when they have a different layout or they have different members and stuff like that, that's when you really need to get a little more clever. So of course, nobody learned anything so far. There is a solution for that. It's called inheritance, right? So the way inheritance works, and I mean nobody's going to learn anything here, but what I want to really emphasize is the fact that we have a physical relationship between the base class, the vehicle here, the interface, right? We have a physical relationship between that and the derived classes, the implementations of that interface. And the physical relationship is that of being a part of. The compiler is actually going to put a vehicle at the beginning, roughly speaking, at the beginning of your car or your truck or your plane or whatever. And of course, right now the vehicle is empty, right? There's nothing to put there. But actually, it's not empty. It's a pointer to a Vtable. So my point is, with inheritance, you really have a strong physical relationship between the implementations of a model, of an interface, and the description of the interface itself. And that's simple, it works, and it's nice, but it also has a couple of drawbacks, which is, I guess, the motivation for this talk. So like I mentioned, under the hood, the way this works is basically by having so first of all, usually because you only have you have basically a derived class, and then there's, you're going to manipulate this whole thing through a pointer to the base class usually, right? So that's why I have a pointer to a vehicle here, because typically what you need is basically a pointer or a reference to a base class. And then that base class actually has a pointer to a Vtable. And then in the Vtable, you have function pointers, which represent the concrete implementations of the methods for that interface, right? And then you can have any set of members in there. We don't even know about this. It doesn't matter. What we care about is the fact that the middle box here, you can pass that middle box to any of the methods in the Vtable, and it's going to just work, because the right function pointer is in there. Am I making sense? Okay. So like I said, there is a bunch of problems with inheritance, right? And the goal of this talk is not really to go too far into these problems, but I still want to I need to motivate this talk. So we're going to look at a few of them. So the first and most obvious one is that it bakes in reference semantics. One of the things I really, really love about C++ is value semantics. I love having an object, right, and being able to make a copy of it. And then these copies, they're disjoint. I can modify the original object, and I know that my copy is not modified. That's really, really powerful. It's really important. So when I try to reason about a program, that's what I need, right? If I were to modify the copy of the object and suddenly it modifies the original one, oh boy, that would be confusing, right? So when you start dealing with pointers and references, you lose that property. Because when you make a copy of your vehicle putter, you're just making a copy of the pointer, right? You're not making a copy of the original value you're pointing to. So you lose reference semantics, not necessarily when you use inheritance, but it strongly encourages you to actually lose reference semantics. If you want to not do that, if you want to conserve value semantics, then you have to basically implement like a clone method, or raise your hand if you've done that before. Okay, right? So you know what I'm talking about, and that's fine. That it's fine, and typically it returns like a pointer that was basically nude, right? And then you can just create a new a new object from that. But what you're doing when you do that is you're basically implementing copy constructors by hand. It's just rolling your own kind of value semantics, and then it's very verbose. You have to clone. And you get into other problems we're going to talk about in a minute. So although you don't need to do heap allocations, right? You could technically create these objects on the stack if they're lifetime, if they don't need to escape the scope of the current function. Or you could use pool allocators, or you could be arbitrarily clever as to how you're creating these objects. So it might not be very, very expensive, but you're still doing heap allocations or some sort of allocation somewhere. Because you need to basically just hold a pointer to some resource that's somewhere, and that's going to outlive the scope of the function. So in like 95, 99% of the cases, you're actually just going to say new, and you're just paying for the allocation under the hood. Another thing, which is inherent to using pointers, is that suddenly you have a null state everywhere in your program. Because, so like what I wanted to do is just say I have either a car or a plane or a truck or maybe something else. And what I end up with is I have either a car or a plane or something else or nothing at all. And that's really, really bad, because now I have to check whether it's nothing at all the time. Or I don't check and then I'm, playing with fire. So that's, that's a very unfortunate side effect of using basically pointers all over the place for runtime polymorphism. Of course, when you start having memory and allocating and having pointer objects that outlive the current function and so on, you end up with like ownership questions. I don't want to say issues, but they're just like legitimate questions you now have to answer. And you don't have to answer them when you're just in value semantics world, but now you do need to answer them. So should I use a raw pointer? Is it like something that I don't own, someone owns it? Or maybe it's a unique pointer, I'm the sole owner of that object. Or maybe it's a shared pointer and then we're all friends with each other. So you kind of have to start answering these questions. And of course, in theory, I would say, like modern C++, blah, 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 use unique pointer, it's the best thing. But I know that concretely, I work for Amazon, so like if I grab in Amazon's code base, I know what's happening, right? And what's happening is boost shared pointer, because most of the code has been written a long time ago, right? So there's a lot, like I'm sure many people can relate here. Like there's a lot of places where we could be using unique pointer, but it's either too inconvenient because you can't copy it easily, and like not all interfaces are written with that in mind. So either it's not convenient enough, or maybe it's just like not supported because you're on a legacy or on the C++ L3 compiler, or there's all these reasons. Or maybe the code was written a long time ago and it needs to stay ABI compatible. You just can't change it. There's like so many reasons why you can't necessarily do the right thing here, but in many cases you can't do the right thing. So, right, and then there's all these other cases in which you're just gonna basically use a raw pointer, and boy, you shouldn't do that, but we all do it a little bit, right? So anyway, you end up having to answer these questions when you really shouldn't, in my opinion. Another thing is it doesn't really play well with algorithms with a standard library. Imagine you have a vector of vehicles, and well, now you just have like a vector of pointers to vehicles. You can't just sort that, for example. You're going to have to sort that based on a custom comparison, and you're going to have to do more work basically because nothing works out of the box when it's pointers, right? In other words, what I mean is in many places where the right thing would just work, if you were using normal value semantics, suddenly it doesn't work anymore. You have to be much more explicit about what you're doing, and it's actually really painful. And also it's intrusive. Because of this physical coupling between the derived class and the base class, you actually have to go back into the type and say, hey, you start with this base class. And that's very intrusive. Like if it's a third-party library, or if it's some code which needs to be to stay ABI compatible, you just can't do it. There's just no way you can do it. You just can't go and change it. So you end up being unable to, like conceptually, you just wanted to say my motorcycle, or no, his motorcycle is actually an implementation, a valid implementation of my vehicle interface. But you can't do it because you would have to go and change basically the motorcycle to do that. So that's it. I'm not ranting anymore, but I hope there is, like Sean Parent is much better than me at, explaining why inheritance is bad. But so you should definitely go watch that talk. By the way, this is one of the best talks that I've seen in my life, so definitely go check it out. But I hope this at least motivates, basically the basis for why we're going to spend about an hour now talking about this. And so if people still have questions as to, maybe questions about the problems that I just mentioned, go ahead and ask them right now. Okay, sweet. So at this point, I'm going to assume that everyone thinks inheritance is, fundamentally flawed, and we need to find a solution for it. So conceptually, what I wanted was just this, okay? What I wanted is, and that's obviously pseudocode. So what I wanted is to say, I have a vehicle, it's an interface. It does not specify any implementation, okay? And then I have arbitrary types, which I may not know about up front. I have arbitrary types, and so long as they satisfy the interface, I should be able to use them where I'm expecting an object that satisfies this interface. So then I could just say, for example, I have a vector of vehicles, okay? And I can just throw in anything that satisfies that interface. And I actually get an object. Like, I don't get like a, I don't care how it's implemented. It may allocate under the hood, it may not allocate under the hood. That's, we're gonna talk about this later. But the important point is that if I have a vehicle and I throw in a car in there and I make a copy of that vehicle, it's actually making a copy. It's working, as you would expect. Does that make sense? Any questions or anything? Yeah.
So for clarification, if we were working in a language where we always had handles that are the same size, then that would be in the direction of what you're talking about. Is that the idea that the handle is the same size, and a vehicle and a car and a truck are all the same size, so we can have an array of 10 of them, and there's no problem. We can copy them, and then we're going to get I hate this term, deep copy, and we're going to get that, but we don't use that word.
Yes. Okay, so the comment or question is, where I'm getting at basically is, I want to have a single handle that has, always the same type word, whatever I throw in there, right? And that way I can have an array of those, or a vector of those, and then when you make a copy, you get a deep copy, but don't talk about this, right? But essentially, yeah, that's exactly what I'm talking about. That's exactly what I'm talking about. Which is a little bit what stud function does, for example, right? You can throw in, you have a stud function, and you can throw in lambdas with different captures or different, function objects that have different sizes in there, and when you make a copy, it actually makes a deep copy, and, and it just works as expected. So yeah, that's exactly what I'm talking about. Of course, I don't think this should be the default in your language, but this should be a facility that is available for when you actually need to pin down the representation of something, because it needs to be used, in a polymorphic manner. So that's what I want, roughly, right? And so the remainder of this talk is going to be about ways you can implement this magic keyword interface. Okay, so if that doesn't seem interesting to you, no offense, you can just walk out. But the rest of the talk is essentially going to be talking about, I'm going to present, I think, 5 different ways we can implement, this interface keyword. It's actually a fairly, rich design space that I don't think it has been sufficiently explored so far. All right. So like we saw with inheritance, the way it works, basically you have a pointer to a base class, and then there's that leads you to an object that has a pointer to a Vtable, and then the Vtable contains function pointers that you can basically do an indirect call on and get the right implementation. So the way I'm going to approach a problem is I'm going to try to separate 2 things. I'm going to try to separate the way the data is stored. So like here, the way the string and the int inside my car, the way these are stored, and the way I do the virtual dispatch. I'm going to try to look at these as 2 separate problems. You'll see this become more clear later on. So the first way we can basically solve that problem is by using something that's typically called a fat pointer. So my vehicle is basically a pointer to a Vtable, right? And a pointer to some data, to just some arbitrary data. Like, I don't know what the actual underlying representation is going to be at this point. And then concretely, when you throw in a real, say, a car in your vehicle, you just assign a car to your well, you allocate a car and then you assign the pointer there. So you fixed your vehicle representation. It's just a pair of pointers, and one represents, how you are implementing the behavior of the type, and the other one basically contains what the data is. So that's pretty simple. So you could implement it roughly this way, okay? So, and again, I'm not expecting anyone to go and type that and do that by hand. It's just to give people a grasp, this is not magic. You can actually just do this. And the compiler is doing something a little bit similar under the hood, right? The layout is different, but they're actually creating structures and whatnot, right? So conceptually, you have basically a pointer to your Vtable and a pointer to your data, and then when you construct a vehicle from anything that has an accelerate method, for example, okay, you just, well, first of all, you set the Vtable pointer to the right Vtable. I'm going to show you on the next slide how that Vtable is defined, okay? So just assume you have a Vtable somewhere. So I'm just getting a pointer to that thing. And then you basically make a copy of your vehicle, right? And you assign your void pointer. You assign that to your void pointer.
Question. It looks like this is a slightly different variation on the Pimple algorithm with a pointer to a base class and then managing it back. Is there a reason why you've taken the Vtable out of the implementation? So because now you have to manage the Vtable yourself, whereas you could allow the compiler to do it for you. Is there a reason the Vtable is moved up, is promoted to the
Yes. Okay. So the comment is this seems like a variation of Pimple where I'm managing the Vtable manually, basically. Yeah, that's true. The reason why I'm doing it that way is you'll see later on that I can actually have. There are different implementations for that storage. I don't necessarily have to have a pointer to the data. I can be more fancy than that, and so that's why I'm really. You will see, I'm basically going to present different ways you can store. So the first one is just on the heap with a pointer, but then there's other tricks we can do. And the Vtable pointer is always going to be the same. And then in the second part of the talk, we're going to see how we can actually change the Vtable pointer to something else. So I'm kind of looking at it from two different perspectives. It's going to become more clear in a second. So yeah, so you basically have a pointer to your Vtable and then allocate your object. The copy constructor, you'd basically implement something like a clone, right? Under the hood, you'd go and basically create a new object called the copy constructor of the underlying vehicle. So the copy constructor would have to live in the Vtable somewhere. And then when you call accelerate on your interface, you just call the accelerate from the Vtable, and everything just works nicely. And for the destructor, well, you need to put something in your Vtable that's equivalent to saying your destructor is virtual, basically. Questions? Okay, so the Vtable is just a struct, really. It's just a struct with function pointers. And then you can initialize it by saying, if I have a T, a concrete type T, a Vtable for T contains the following functions. And here I'm using lambdas, right, to do that, because lambdas they will nicely get converted to function pointers when they're stateless. So here what I'm doing, basically, I'm just creating a Vtable which contains these two methods, and each method takes a void star, which is this, which I don't know from the outside. The code that's calling into this Vtable doesn't know what type it is, but I know what type it is because I've been created with a concrete T here. So I just static cast to the concrete type that I know, and then I call the statically dispatched method, right? And well, that's it, right? So basically that's like a thunk. Concretely, the code that's generated goes like calling you with a void pointer, and then perhaps doing an offset calculation, but in some cases it might actually be nothing at all, and then just like another call to the statically dispatched method. Does that make sense? Okay. And so I wrote a little library. Like I said, I love to push the language a little too far. So I wrote a library actually which does that. And the goal of this talk is not to present the library. It's to present the ideas behind it. But the general idea is basically that you can define an interface. There's like a little domain-specific language you can use to define an interface. And it's nowhere as nice as just saying interface vehicle, blah, 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 of course, right? But the idea is the same. And then you can basically do virtual dispatch by using this little notation here, poly.virtual accelerate _s. What this does under the hood is this _s is a compile time string. Okay, and what you're doing is at compile time, you're asking the library to go into so the library generates a Vtable under the hood. There's lots of metaprogramming, and you're basically asking like, go get the right entry in the Vtable at compile time. So it's like a map lookup, but it's like O1, or it's like not even, it's basically just the same as a struct access in terms of runtime. And the one thing I really want to point out, the important part of this is look at the part that's underlined here, the remote storage. So the library, because we're going to see a bunch of different ways we can store the object, the library actually allows you to specify a policy that you can use for the way you're going to store the object. So right now we're using the remote storage, which is basically just I have a pointer to something that's remote, that's like on the heap. Okay? That's really the important point I want people to focus on, yeah.
So the important thing about virtual functions and why they're slow is not the indirection of the pointer, but because computers' hardware has trouble following an arbitrary pointer that it can't foresee. So if you're going through a sequence, for example, you can predict what the next thing is going to be. But when you have a pointer, regardless of how you access it, whether it's order 1 or whether you have an indirection, whatever, some extra thing, the point is that the virtual table is harder for the computer to optimize. So what I was going to ask is, with this heavily templated metaprogramming thing, do you have the possibility of inlining the function in the virtual table, or are we still going with the point?
Okay, so the question, if I may summarize it, is do I have, with all this metaprogramming stuff, do I have the opportunity to inline something that I would not have the opportunity to inline if I were using virtual functions, correct?
Yes.
Okay, the answer is no. It's impossible to, well, no with caveats. Yes. It's impossible to like, at the end of the day, what this code generates is exactly this code, okay? And this code. Well, not exactly, but you get the point, right? It gives you exactly the same assembly, okay? And this assembly does not allow you to inline more than like a normal indirect call.
Okay. Except
in some cases, which I'm going to talk about later. But unless you're lucky, no, right? Unless you're lucky, you're hidden behind an indirection. Whether it's like 1 or 2 or 3 indirections, it might not be possible to inline, unless you get lucky. Yeah, so the main point is you have this storage policy, and also the virtual dispatch here, because I've got some people before that thought this was like a std map lookup. It's not, okay? It's just like a struct access, even though I'm using quotes and stuff, not creating strings here, okay? This is all compile time magic. And yeah, you have this DSL, this domain-specific language to specify an interface. So I'm actually using this as an example of why we should probably get something in the language, because nobody wants to write this, right? And this is pretty much as nice as you can get. And it's not really, really nice. But essentially, I say that a vehicle needs to be copy constructible and destructible. So this says the Vtable is going to have to contain like a copy constructor, a destructor, also an accelerate method, which has the following signature, like it returns void and then it takes a reference to something, right? Yeah, and then I specify what the implementation is. So anyway, I'm going to fly over that. So. Mainly the strength and weaknesses of having the remote storage, right, is that, so the strength mainly is that the model is very simple. It's very close to just normal inheritance, right? So it's easy to reason about, but it always requires an allocation. But there's different things you can do here. And now the whole trend of the talk is going to hopefully become much clearer. So you can be more clever. You can say, for example, instead of always having a pointer to something that's allocated on the heap, I'm going to have a pointer to something that's allocated on the heap, or if the thing that I wanted to assign, like if the concrete implementation was pretty small, I have a buffer with like a couple of bytes there. And if it's pretty small, I'm just going to throw it right here, right in there. And the pointer is actually not going to be pointing to anything, OK? So that's called a small buffer optimization. And it's actually, so who knows about small string optimization? OK, so small string optimization is just an instance of this general pattern, right? Where you have something which is a fixed size, and then you can go like, oh, well, actually, I can pre-allocate a little bit of space, and if the thing I want to put in there is pretty small, I'm going to be able to skip the allocation. So the idea here, and this is a very naive implementation, of course, I still have my pointer to the Vtable. Don't worry about this. And then I have basically a bool or just one bit of information stored in any way possible, right? That tells me whether the thing is on the heap or whether the thing actually did fit in my small buffer optimization. And then I have a union, which is either a pointer to the thing on the heap, or it's into a buffer of size n, which will contain my object if the object was small enough to fit in there. Okay? Does that make sense for everybody? Okay. So the way it works basically is when you get, right, okay, so this is how you can implement it. Basically, you still have the Vtable pointer, and then you have the union. And the interesting part is in the constructor, okay? In the constructor, you know what concrete type you are being initialized from. That's where you go like, I have a vehicle, I'm throwing in a car in there, or a truck in there, or a plane in there. And that's where you know what the type of the object you're going to be holding is. So you know the size of your buffer also. So you say, OK, if the thing fits in the buffer, or I guess if the thing doesn't fit in the buffer, that's the first branch of the if here, I'm on the heap and then assigned to the pointer. And otherwise, you say, I'm not on the heap, and you do a in-place new here. So in-place new, for those that might not be familiar with it, is basically just you provide a pointer, and you're going to be calling the constructor of that object on that area of memory, essentially. So you're basically just constructing an object at the place which is pointed to by the pointer. So in this case, I'm constructing at the beginning of my buffer, I'm constructing an object there, right? And then when I want to call a virtual method, I say, well, I go to my Vtable, and I get the actual implementation, right? I get the actual method that I want to call. And then I call it on either my pointer to the heap or the beginning of my small buffer, depending on whether it was on the heap or not. So that way, if you have like a wide range of objects, like of all different sizes, but you know that most of them will actually fit in, like there's only maybe a couple of them that are very large. In most cases, they're pretty small. Okay, so then set a buffer size which is around that size. And most of the time, you're going to be eliding the allocation. And in the other cases, well, of course, you're going to get an allocation. So it's a nice like in-between kind of compromise. And there's different ways of implementing the small buffer. So instead of having a bool, I actually recommend against using the first one I showed, which I guess means I should not be presenting it first. But another way you can do it is by having, you can actually store the bool here in the Vtable. Or even better, because like for a given type, it's all in a given buffer size and a given type. For a pair of these, it's always the bool's always going to be either true or false. So you can put it in the Vtable, or you can even do better. You can populate your Vtable, and the functions in your Vtable have the knowledge of whether what they're being called on fits in the small buffer or not. So you don't actually need a bool there. Yeah.
the translation unit and the for declare, you actually have to know the size.
Yeah, the comment is, yeah. Yes, so the comment is you need to know the size of your implementation. So like you need to know the size of the car or the truck or the plane in advance. That is correct. You need to know it when you are generating the Vtable, basically, right? In this case, or when you are generating the type erased wrapper, which is the vehicle type, rather, I should say the constructor. When you're calling the constructor for your vehicle, you need to know what is the the end type. You need to know the complete type basically of the implementation. But that's usually the case because you're constructing it at that point from something. So you should know the object because you have an object and then you're throwing that car or that truck, which you have constructed. You're putting that into a vehicle. So you ought to know already the size of it. But yeah, that's true. So yeah, you can actually inline the knowledge of whether it's on the heap or not into the Vtable. Another way, which seems to be I ran a couple of benchmarks, and this is honestly very difficult to benchmark because it's very micro, and I'm not like a super low-level person, so I kind of did my best here, but roughly speaking, this seemed to be the best. You want to try it out yourself, of course. But the idea here is you have a pointer, which always, and that's always what you dereference whenever you want to get the storage. But the pointer either points right after itself into the small buffer, or it points somewhere on the heap. So that way the dispatching is like very trivial. When you want to dispatch, you just go and follow that pointer all the time. But what you don't know is the pointer might be leading you somewhere on the stack, somewhere on the heap, or right after the pointer itself. Okay? And so far, I think this is the best I've seen. But and so with the library, what you can do is just change you just change the storage policy. So like I said, you can specify multiple storage policies. So in this case, you can use like SBO storage 16, which tells it, use a small buffer size with 16 bytes, and that's it. You can change, number of bytes, of course. So you just have to change that part, and then crazy metaprogramming, blah blah blah, and then the code that's generated under the hood is the same. So the one cool thing with this is that it does not always require allocating, right? So that's very positive. But it may take up a little more space. If you're not using your small buffer very often, then you might be wasting a little bit of space. And the other thing is implementing copy, move, and swap operations is kind of more difficult here because you have to consider whether, you have two things. You have the target and the destination in these operations, right? And you need to check whether, you basically need to check for all, especially for swap, you have to check all the combinations of what if the left-hand side is in the small buffer and the right-hand side isn't? What if both of them are in the small buffer? And so you have, to handle all the combinations. So it's kind of a little more expensive, but maybe you're not swapping that often, so might not matter. But they're a little more complicated to implement, dispatching may be a little more costly depending on how you do it as well. Like for the bool implementation, you're taking up a branch every time now. Maybe prediction works properly and you don't care, but anyway, there is a little more code there. Yeah.
That could also mean your move might have to allocate, which could be a problem. If you're moving something that was in a small buffer to an object that isn't big enough, it wasn't in a small buffer, you're moving into an object that it's not big enough for, you're going to have to allocate it.
So the comment is, it might mean that your move needs to allocate, because if you're moving something that was in the small buffer into something that wasn't.
The target was. The thing you're moving is too large for the small buffer, but the object that was originally allocated as the target didn't need an allocation because its object was small.
Okay. So. No, but what you're saying is true. Your move might need to allocate, I think, in case you're, but okay. There's like two answers to this. The first answer is no. If you only allow vehicles that have the same small buffer size, you know, to interoperate, then you don't have this problem, because if it fits in the small buffer, then you just, you know, move into the small buffer. If it didn't fit in the small buffer, then you just steal the pointer, right? If you are allowing vehicles with different small buffer sizes, or, you know, interfaces with different small buffer sizes, then you can get in a state where the original thing had a larger small buffer size than your destination one. And then, so you're not expecting, yes, exactly. Then you would require indeed, like, an allocation for that. Yeah, which might be a problem, but I don't actually do that. I don't allow that in the library, so that's not an issue. But it's important to know about this, because I don't expect anyone to necessarily, you know, use the code as is or use the library or anything. But so, you know, someone that rolls that, if you roll your own, basically, it's important to be aware of that. That's very true. And we can actually push this concept further. We can actually say, instead of having a buffer and a pointer, right, and sometimes be in the small buffer, but sometimes be on the heap, you can say, no, here's what I'm going to do. I have a small buffer, and I only have that. You don't have the alternative of going to the heap. And what happens is, if you try to put something that's too large to fit in the small buffer, it does not compile. That's actually very useful, right? If you're in a environment where, you know, memory is premium, or where you care so much about, like, maybe you're vending this library to a bunch of programmers that don't necessarily have, you know, the knowledge of all the details and stuff like that, but you need to make sure that they don't produce, you know, performance problems, then that's the kind of stuff you can do. You can enforce that statically. You can be like, okay, I'm going to give you this nice tool, but I'm going to make sure that you don't mess up. If you mess up, if you write code that would end up being, you know, potentially, you know, a performance problem, then actually it's not going to compile. So the way you do it is you still have your Vtable pointer, nothing changes there. And then you have a buffer of a fixed size. And, right, and you always do the in-place new in there. And if the size of the type that you're throwing into the type arrays wrapper is too large, then you just static assert, right? So if it doesn't fit, it doesn't compile. So you use here an aligned storage. In this case, I have, you know, 64 bytes, whatever. That's probably too large, but. And then in the constructor here, I initialize my Vtable, and then I make sure that the size of the object is less than or equal to the size of my buffer. And then I go and in-place new into my buffer, right? And then the dispatching is also very trivial. I always just, you know, call my vpointer on my buffer. Any questions? Yeah.
Well, so what you've done here is you put a limitation, which is a fixed size, and that has a spatial consequence, which is that the largest object is going to govern how big the buffer space is. So one of the things that's typical is to have the buffer space be very small and have an indirection, not to an own thing, but to an actual global table. So if you have a spreadsheet, for example, all of your ints and doubles go right into the spreadsheet. When you get something that's bigger that won't fit, then you have an indirection to secondary storage. And that actually makes things smaller, because it means that the maximum size for the object that goes into that space, because it's a variant basically, the maximum size can be smaller, and then your array of things can be smaller. And then it's one of those exceptional cases that require separate storage. So that's another pattern.
It's the second one I presented, I think.
Okay.
Yeah.
Okay.
So I think what you're saying basically is you either have storage that's remote somewhere else, or you have a buffer of a given size.
It's a variant of the other one, where it's not like on the heap. There's secondary storage. In other words, you've got a facility like a spreadsheet. And then the table consists of in-place data or a pointer to something that comes along with it, so that the whole thing is wrapped up in a framework. But it's not global. It's a thing. But that particular data structure is very efficient for doing spreadsheets. So it's a little...
So would it be similar to saying that you have basically the small buffer optimization where the fallback points into like a pool allocated thing?
Something like that, yes.
Okay, yes. Yeah. So nothing prevents you from using a custom allocator to implement the small buffer optimization. There's one thing that I should have mentioned that, but there's one thing you don't get with this, which may or may not be a problem, but when you use a pool allocator instead, because that's a comment I've gotten before, is why don't you just use a pool allocator and be done with it, right? And no, that's a very fair comment. So one of the problems, besides the fact that you might not, want to start using allocators everywhere, this is maybe if we had a language facility for that, that would be really easy for any beginner programmer to use. But besides that, there's also the fact, let's say you have a vector of those, and then you sort the vector, right? If you're actually storing if you're actually storing the small buffer right in the object, then the data, follows it, right, when you sort it, which means that you don't get out of order accesses if you re-access the vector afterwards. So let's say you have just pointers into some memory that's been pool allocated, okay, and then you sort them. Suddenly, and then you go and traverse your vector again. Suddenly you're traversing, in a non-contiguous, you're traversing your vector and accessing memory in a non-contiguous manner because you sorted basically pointers into your original.
So to paraphrase what you said, the data that's local is sorted so you can traverse it linearly.
Yeah.
But when you go to access it via the pointer, that data stayed in the same position.
Yeah.
So now it's out of order with respect to the traversal of the heads of
That's correct.
the objects. That's actually a very good point.
That's correct. Did everybody get that? Should I try to, this was very well phrased. So I'm going to try to phrase that as well as you did. So what you're saying is basically if you access the data through a pointer and you sort it, now you are not accessing it in the same order.
How about this? Let me give it a shot.
Yeah.
Imagine that we're dealing with strings that are handle bodies, so there's no short string optimization. Now, when you allocated it originally, what you're doing is you're creating the strings in order, and the bodies of the strings are getting put in secondary storage in order. Everything's in order. You traverse the strings, the caches are great. Now, you sort the strings, say it's a big table. Now the heads are in a different order, the string bodies are out of order with respect to the new order of the heads, and now you get the problem with having cache misses. And that is a very good point.
Okay, so third time I'm trying to do this. So essentially, if you have the handle to the data and the data not exactly in the same place, if you sort it, then the storage for the data itself does not necessarily follow the order of the handle that you're using to access it, which means that you might get out of order accesses. Not as well phrased as you, but
the point is important, so I'm glad you made it.
Yeah, okay. Made it 3 times also. Alrighty. Okay, any other comments or questions? Yeah, go ahead.
You might put it that way that the storage, the allocated storage remains in order, but your pointers are shuffled.
Yeah, okay, so the allocated storage remains in order, but your pointers are shuffled, which means that if you traverse in order, your pointers in order, then suddenly you're accessing shuffled, in a shuffled manner, the memory, which is not very friendly. Okay, so with the library, you can implement this new storage policy by just saying use local storage with whatever size you want, right? So it's also pretty simple. So I would really love for us to have a language level facility that allows us to do something like this, right? To just say, here's my interface without having to use this crazy domain specific language, please, right? And then have all of this nice flexibility in defining how it's implemented. For example, like other languages like Rust, for example, they have traits, right? And the traits are very similar to that, where you can specify like an interface essentially, and then you can pass arbitrary types that satisfies this interface. And they do type erasure under the hood. And when I asked one of the Rust guys how it worked under the hood, he told me I think they use fat pointers, but you don't have control over how it's implemented. So it's really cool, but you don't have control. I would like us in C++ to get something where we actually have control over how it's implemented, because it's possible to do it. Here's a library that does it. So if we get a language level facility, which I hope we do, because I'm going to work on it, it needs to be at least as good as this. So the cool thing here is obviously we don't ever get an allocation. Like you are statically ensured, like you are assured at compile time that you will never get an allocation, right? And if you were to get an allocation, instead you get a compiler error, which I absolutely love, because I like finding problems before they happen. And the dispatching is as simple as it gets. You're always just calling the virtual function on just a piece of data that's right here. But it may take up more space. So basically that's the point that John made here, is that the size of your object is governed by the size of the largest object that you might want to put in there, which might be wasteful in case you have like one really, really fat object and then most of the objects you put there are very small. So it's not always a great fit. So I have 2 questions. Go ahead.
And the drawback is you no longer have an open set. Because there are places you don't know the biggest size in a head. Right. So you violated your initial restriction. I can now use a variant.
That's actually not true. So the comment is, now you no longer have an open set, so I violated my initial goal here. I don't think that's true. You have you don't have a closed set of types. You have a closed set of sizes. It can be 0, 1, or blah, 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 up to n, where n is the buffer size. But you can have any type, so an open set of types, so long as the size is within there, which is actually a big difference.
It is a difference, but still a restriction.
It is a restriction, that's for sure.
It's not open.
That's true, it's a restriction. I had another question, yeah.
Basically, you can reopen it by allowing the user to use something like the simple idiom, so they have a small object or a small object handle that they pass into the vehicle. It puts the work of the memory management on the user, and it's optional, it's opt-in and not built into the vehicle.
Yes, so the comment is to regain that the openness of the type, then you can just ask the users to use a pimple basically, so it fits. But then I would say use SBO in the first place. Use small buffer optimization. So the second technique I showed. So I'm going to move right along just because I just watched the time and I've just got 30 minutes. So just a quick benchmark here. I'm allocating a bunch of objects. You might not be able to see the titles here under I'm going to go basically from your left to your right, okay? So I'm just creating a bunch of objects which have 16 bytes. I'm using Google Benchmark, so it iterates. So I'm creating a bunch of objects, and it does that many, many times until a variance is satisfactory, okay? But still, we're not going to draw like really drastic conclusions, okay? You'll see. So with inheritance, so that would be, well, I'm basically allocating all the time, right? And I'm throwing something in there, making a heap allocation, and it's kind of expensive. Then if I use remote storage, which is the first storage policy we looked at, I also make an allocation, so I pay for it. For SBO storage with 4 bytes, that's the third one from the left here. SBO storage with 4 bytes, because it's 4 bytes and my object has 16 bytes, it does not fit in the SBO, so I need to do an allocation. And you see that the timing is pretty much the same. The fourth one from the left is the SBO storage with 8 bytes. Again, it doesn't fit, therefore I get an allocation. And suddenly I used the SBO storage with 16 bytes, and now it fits. And guess what? No allocation. So essentially what this benchmark is showing is allocating is more expensive than not allocating. So like I said, no drastic conclusions. And then I've got the local storage with 16 bytes, which also never makes an allocation, and it's cheap.
You were using the global allocator when you did.
I was using the global allocation when I did that. The picture would be serially different with a pool allocator, for example, or with any other fancy allocator John Lakos might come up with. But yeah, nonetheless, using allocators have the drawback that I tried to word, thrice before, which is, about reordering and stuff like that. So I guess rough guidelines, use the local storage whenever you can afford it and whenever it makes sense, or if you don't need to, if you don't mind the size of the storage being part of your ABI, so if it makes sense, then it's going to be faster, right? But otherwise, use SBO with something that makes sense, with a size that makes sense, which is sometimes just the size of pointer, for example, because this is always free, right? You either have a pointer or some storage. So you might as well make that storage the size of the pointer that you have anyway. So in other words, if you have something really small that would fit within the size of a pointer, then you're not really losing anything. And use purely remote storage just basically when the object sizes are so scattered, or when you need really the minimum size for your handle. I guess that, or maybe you're using a pool allocator and actually it doesn't matter that much, so then don't complicate your life. There's another thing here. We're going to leave the realm of value semantics though. So before, we were making deep copies, but don't talk about this word, right? Don't say that. But you were making deep copies essentially. Now we're not doing that anymore. So I'm going to go from string to string view, okay? In other words, essentially what we do here is we have a pointer to a Vtable, that doesn't change. And then we have a pointer to something that we do not own. So it's a pointer to data, but we don't own that, okay? And it's like a polymorphic view. It's actually really cool. It allows you have an object somewhere, and you can imbue arbitrary behavior, arbitrary runtime behavior to some data that already exists elsewhere. So here in my main function, I create a truck, and then I pass that truck to my process function, which takes a vehicle ref. There's no copy being made. Previously, in the previous slides, you would have made a copy, and then you could pretend from within your process function, you could say that's actually a copy. It's a disjoint copy of of my truck. Actually, I don't know it's a truck. It's just a vehicle. But now you know that it's basically like a lightweight view over the original object, which absolutely you're shaking your head like this, but we standardized. Or we are about to standardize for C++20 something called function view.
Yeah,
and
the nightmares becomes worse.
Nightmares becomes worse, right? That's what he says, but I think it's really useful anyway. So you can implement that by, it's really, really easy actually. You just have a pointer to some data, and then when you initialize your vehicle ref, you just take the address of whatever you're being passed. So notice that in my constructor here, I take a reference to the anything. So the reference here is really important. So I'm taking a reference to the thing that I'm being passed, and then I hold on to that. So of course, you don't want a vehicle ref to outlive the thing it's referencing. It's the same as like a string view or function view that we're going to get soon. Yeah.
Have you retained value semantics?
I have not retained value semantics here. That's why I'm leaving, like I said, I'm departing the realm of value semantics now. It's kind of this one's a different beast. I'm not claiming it's the same as, but it's still useful. And the cool thing is, actually, you can still implement it by just changing one line, right? You can just change the policy for storage, basically. Oh, okay, I lied, 2 lines. You also need to take a reference in your constructor here. But if you take a reference to your constructor and you use the right storage policy, non-owning storage, then you basically have this is it. Another thing you can do is shared remote storage. So you can, like, now I'm like, this is the 5th one, right? And it's just me, right? Like, there is probably a dozen different ways that we can implement this. This design space is super rich. It's super interesting. So shared remote storage is basically where you're using shared pointers under the hood. And that way you can make copies of objects and, well, I mean, they're all, you know, they're all actually pointing to the same thing, which means that you can have, you know, fancy lifetimes there. So you implement it by just using a shared pointer, essentially, shared pointer to void. The really interesting part, because that's kind of weird if you're just sharing objects around, but where it becomes really interesting, and this is something that Sean Parent actually presented before, is if you do copy on write. So whenever you call a method that is const, okay, you just use the object that you have a shared pointer to. You just do that. If you call a method that is non-const, you make a deep copy of the thing that is inside a shared pointer, and you get a new shared pointer to that. What this gives you is actually value semantics, because so long as you don't modify the thing, you are sharing the same data, okay? But it's fine because it's a const, basically you have a const view over the data, okay? And as soon as you modify it, because that would break, because you're using references, that would break value semantics, well, now you make a copy, and you modify the copy in place, right? And then if you make copies again of that thing, you just share the pointers until you need to modify it again. So that's actually really nice, because if you have objects that you would like to share because they're large, and very expensive to copy, or something like that, it gives you a really easy way to basically to have a purely functional, almost, right? It's almost as if it was like a purely functional data structure where you can assume, once you get a copy of something, you can assume it's never going to change, right? It's a const object. But actually you can modify it. It's just going to happen to modify a different version of it. Am I making sense? So this is actually really great for you know, concurrency. Yeah.
If I'm not mistaken, this is actually implemented in GCC's string.
Yeah.
Right?
Yeah.
It has problems because it leads to data races when you don't follow strict constraints. There is a bug file again.
So the comment is this is what GCC string used to use. Yeah, that's right. Yes. Copy on write. Yeah. It has problems if you're not following strict const correctness. That's true. If you're using like const cast anywhere in there, you just, you know, oh boy, good luck, right? Yeah. And I mean, there's other problems. Let's say. What was it? We had a problem actually at work where we had pages that were, essentially we were making copies, and because there was a ref count in there, we were copying pages all over the place, right? Into shared memory that should have been shared by different processes, you know, like nastiest nightmare ever, right? We were making copies, and because of that, we were duplicating pages that should have been shared by multiple processes, and then you're like, why am I taking so much memory? All these processes are sharing the same memory. What you don't realize is when you make these pages read-only, and you start getting page faults, now you're like, oh boy, that's, right? Like that's what's happening. So yeah, this is really subtle. So you know, if you don't know what you're doing, or this is not the right thing for all cases, but there are definitely cases where this can help. Yeah, real quick.
It's a nightmare for concurrency because if you concurrently copy objects, you're getting out of order in your program performance, and that's why we disallow this implementation for strings now since C++.
Can you repeat again?
So if your counter has to be synchronized on each copy, and that's a nightmare if you use your data even in single-threaded environment, because incrementing and decrementing the counter is a very, very expensive operation.
But it might be nothing compared to actually copying the data.
It might or it might not, but we have enough experience that.
But you might not want that in a standard library, but for custom user applications,
it might be okay. I just want to point out that that's the reason we forbid it since C++ 11 as an implementation practice for strings.
Okay, so it might not be the right approach for strings, but for sure it might be, actually I'm just replaying Sean's talk here. He had he worked on Photoshop. He had this image that was like a gigantic, or this document which was like a gigantic, super expensive thing, right? And basically that's what they did under the hood, and apparently it was a miracle. So just watch the talk because, yeah, it's really good. So, it's just like another implementation. Right, you can use, what was that? Okay, so just do copy on write, and so it allows sharing potentially expensive state. It interacts nicely with concurrency in some cases. Okay, but it allocates, and there's ref counts, so you have to be aware of those. There's like a bunch of pitfalls with that. Essentially, the pitfalls that exist with shared pointer also exist with that approach, but they might be even harder to diagnose when you fall into them. But we're C++ programmers, so use the right tools when in the right time. That's what I would say. But maybe I wouldn't do that for std string. It's a general purpose class, so it might not be the right choice for that. Okay, let me show you why you care about all of this. So maybe you've heard about std function, hopefully. And hopefully you've heard about function view, maybe. This is coming for C++ 20. Basically, it's just a view over a std function. It's a std function that does not actually own the callable that it's referencing. And there's another thing that I think is SG14 that is considering this. It's called in-place function. In-place function is a function that never allocates. Okay, and guess what? It has a fixed buffer size. So in-place function is basically just has a buffer, and it throws in the callable that you put in it in the buffer, and it doesn't compile if it's too large. So you can actually implement it that way. You can say I have a basic function with a custom storage policy, then use Dyno or any fancy thing under the hood, and then here's all of these proposals, right? Roughly speaking. So a function is just a basic function with a SBO storage, because actually std function, in most implementations, it uses SBO today, right? The small buffer optimization. In-place function just has a local storage policy. A function view just has a non-owning storage policy. And shared function, I'm not sure that's useful, but you can do it. So, but really, like the three first ones, that's pretty cool. So because we see that pattern, and we see, like, for function at least, people are trying to, they're coming up with new proposals, and they're actually trying to get this into the language and so on. It would be useful I think it's useful to recognize that pattern and to perhaps get a general purpose facility that allows us to capture that pattern, and then we can implement all kinds of type erased interfaces with that. Callable is one. Std function is just a type erased wrapper for a callable interface. But we have any, std any, which is actually copyable. That is the, like, copyable and movable is what any is representing, right? It's anything that can be copied. And there's certainly others like that. Real quick, I'm going to go over vtables, because I said I wanted to look at the storage and the vtables differently. So it's actually possible, like normally we have a pointer to a vtable. It's actually possible to do something else. We have some choices, right? We can actually inline the vtable in the object. If we wanted, we could store the vtable directly, because we're writing the vtable by hand. So we can just have a bunch of function pointers directly in our object instead of having a pointer to those. You can do that. We have, like, vtable policies in the library that I wrote. It's kind of fancy, but it's interesting. You can do all kinds of crazy things with it. But the main point is usually, from my experience, is a pessimization, actually. And the main reasons that I've gotten so far is that if the vtable is in the cache, the fact that it's accessed through a pointer doesn't matter anyway. Like, the vtable's hot, like, whatever. Like, you don't care about this anyway. Plus, if the vtable is in the object, and you have like 1 million objects, well, first of all, you're wasting a novel, a lot of space, but also each object might not be in the cache, which means that it's more likely that you're actually going to get, your Vtable accesses are actually going to be colder than they would be if you just stored pointers to something that's very hot. So usually it's epistemization, a nice experiment, I guess, but no more than that, I think. And you can do partial Vtable inlining. You can say, just these methods in my Vtable are going to be inline. The rest is going to be remote. So my goal with this was to actually get a performance benefit, improvement, which I did not really get. So again, with the library, you can say some of the methods are local, the other ones are remote. And it's not really an optimization. But I have a fun observation about Vtables. And that should be, give it a second. It's a compiler explorer thing. Damn it. I would swear it used to work. Okay, yeah, nice. Okay, so what I want to show here, can everybody see? It's a little small, maybe. Can you see Ivan at the back? I see some yeses. Yeah, okay, so the main point here is I'm just calling, I'm implementing a Vtable in three different ways. The first one is a remote Vtable, so I have this fat pointer, right? And I'm dereferencing the Vtable and then calling a function in there. The other one is a local Vtable, where all of my functions are basically in the object itself. And the last one is using inheritance. And what I want to show is simply that when we have either in the remote case, so where basically whenever we're accessing the Vtable through a pointer, okay, you see here there's two calls, two moves. And here there's two moves as well, and two moves. And two moves. Each of them is a virtual call, okay? Well, is preparing for a virtual call, the call the indirect call here that comes after. The idea is one of these moves is actually reloading the Vtable pointer, okay? And so that's for the hand-rolled remote, and this one here is for the inheritance. So when you have a Vtable, right, like whenever you're doing like inheritance, that's what you end up doing. Whenever you're gonna do a virtual call, you reload the Vtable pointer before you do it. Okay, and notice how in the local case, here there's two moves. You're loading a Vtable pointer once, and then there is one move and one move. You see the difference? Before each call, there's only one move in the local version. So what I was told by Chandler Carruth is that because you don't know, because you're passing this pointer, okay, to your virtual function. And that's a completely blind jump. You're like passing this pointer and you're jumping somewhere. You don't know what this code is doing. It could be actually changing the value of the Vtable pointer. So you have to reload it to make sure that the code is correct. So apparently they just can't do anything better than this. It's just not possible. They have to reload the Vtable pointer every time. It might not be a big deal, but I think it's an interesting thing to understand. Whereas when it's local, because the V pointer is there and you see what happens to it. It's basically you're not going through an additional indirection for that. You don't have to reload the Vtable pointer. You can tell that it was not modified. So that's an interesting thing to keep in mind. Right. And I have another story about inlining, and we're almost done. But I have another interesting story about inlining. So I was writing one of the benchmarks for this talk. And so I had this thing here. I basically type erased an allocator, okay, iterator. So I have this, it's like a stud function, but it's just for iterators instead. So instead of having just a function called operator, it has a virtual plus, a virtual dereference. It has all of these things, right? It's not the most performant thing, but because every time you increment it, you're going through all these mechanics. But it's a useful thing anyway. And so I had this benchmark, which just basically implements like a stud copy over these type erase iterators. And to make sure that the compiler did not just inline everything and just optimize everything out, I just added this little no inline. attribute to the function that creates an iterator. Okay, just to make sure that the compiler wouldn't know exactly what I'm constructing my iterator from. Otherwise, it just folds the whole benchmark, and there's just nothing to benchmark. And I get something like this. So the first one from the left is static dispatch, okay, where I basically know that I have a std vector of int and an iterator over that, and there's nothing, type erased or virtual in there. So super performant. I think the compiler just folded everything. That was it, right? And then with inheritance or with the Dyno remote vtable, I was actually doing some work right here, right? So we expect that. If you static dispatch, then you can do crazy optimizations and everything's fine. If you don't, then you have to actually run the code, right? And then I tried something, just this. So I just took one function, which was not inline before. And it's just like, just a function like this, right? It was not inline before. And now I say, you may inline it if you want. And it's a small one, I'm expecting it might be inlined. And suddenly, I get this. So the left one is static dispatch, as before. The middle one is inheritance, as before. But suddenly, the right one, the Dyno remote vtable, gets folded like the static dispatch implementation. I did not understand why. So I tried to think about why this might happen. And here's the difference. The difference is something that we touched on early on when John asked what was the difference between having two pointers right here and like one to the vtable, one to the data, and one pointer that points to the data plus a pointer to the vtable, right? So in the inheritance case, I have a pointer to my object which has a pointer to the vtable. So I have two hops, right, to get to my vtable. In the remote vtable, because I'm using a fat pointer, I have a pointer to data, which we don't care about for the purpose of this example, and I have a pointer to the vtable. So in order to get to the vtable, I just have one hop, not two hops. And my suspicion is, in that case, this interacted very nicely with like the optimizers inlining limits or something like that, and suddenly the inliner was able to see exactly what I was doing, and it could tell actually, well, you're not doing anything, so let me elide everything, right? Let me elide just not emit any code. And I mean, this code is kind of involved, like there are allocations in that code under the hood and stuff like that. The compiler, because it could inline that function, it could see, I know, I see what you're doing here, right? And it didn't do anything. So I guess the lesson here is that reducing the number of pointer hops can lead to unexpected inlining in some cases, or maybe playing with your inlining limits or something like that. But this can actually, this is very surprising as not a person that works on a compiler or an optimizer. I'm very surprised by that, but I'm pleasantly surprised. And when that happens, giant optimizations become possible. Now, that's a toy example. So in that case, I think the code was just removed completely. But in other cases, if the compiler can actually figure out what you're doing, it might not be able to, like, hopefully your program is meaningful, so it's not able to just remove the code, right? But it might be able to figure out, like, oh, okay, I see what you're doing in that loop. You're calling this thing, but actually that's a virtual function, but I can tell, where it, I can tell what type it's gonna be. Oh, okay, and you're doing some kind of like arithmetic in there. Oh, maybe I can vectorize, right? So you might be able to get some things like, vectorization or, allocation elision, or I think they can fuse allocations, and like all these like super cool optimizations that they can do when they can see the code. If the compiler is able to inline, because because maybe you reduce the number of pointer hops or something like that, then suddenly the optimizations that become possible are just like crazy, right? And it's way beyond just, I guess my message here is just, it's way beyond just avoiding the virtual call. It's way beyond that. Is that suddenly if the compiler can tell what you're doing, it can not only elide the virtual call, but it can start, making code transformations that are going to result in much, 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 larger benefits. Yeah.
So there's a real-world example of what you're talking about, where people have argued against allocators because of the virtual function call. And the classic case where they argue is you have a custom allocator that you put on the stack, and then the next thing you do is you create a container using the pointer to the custom allocator. If the virtual functions are declared inline and everything is all good, the compiler can make the code look exactly as if it were templated. Just the same. So there's no cost. And that is a typical case of the use of a monotonic allocator. So it is not, you know, oh, this is a toy example. It is the real deal. Now, it turns out that even the virtual function call is insignificant compared to the benefits of allocators, and still you can measure it, and you can measure it's going away on GCC. Client is lagging, so client people, please go fix your compiler. GCC's got it right.
Okay, so John mentions that a very real example of this is actually with polymorphic allocators, where there is a virtual call involved, and one of the pushbacks for it is that it prevents compiler, well, the compiler from inlining stuff and reducing the code to basically code that is equivalent to if the code had been templated initially. Yeah.
Have you considered that this result may have been because of the lack of inheritance, that there's the dynamic type of the object can't change, so the compiler can make more assumptions that it would be able to when the dynamic type could change?
So the question is, if I considered that this difference might be caused by the fact that the compiler can tell the type cannot change. No, I think the type could change actually, because I could do like a reinterpret cast and the lifetime of the object and then in place new on top of it or something like that. I might need to get into launder territory though there, but std launder, most people don't know about it. It's a great thing. Great thing that you don't know about it, that's what I mean. Yeah. Launder is not a great thing. But yeah, so I think, yeah, I could change the dynamic type. It would be more work to make it valid though, but I don't think the compiler can assume that from my code. And yeah, so lessons learned from that. So by default, don't mess around with vtables. It's not worth it, okay? Just don't. And if you like see that it's giving you a benefit, then sure, but then you're probably like a game developer or someone in finance industry and you know exactly what you're doing, probably much more than me, right? So go and do your thing, right? But normally just don't mess around with this. One thing that is useful is watch out for places where you're just, you know, a few things away from getting some giant inlining. Either it's like pointer hops or like just the way your code is written, but be aware that sometimes inlining kicks in, and when it kicks in, it's like the best thing ever. And now I'm very close to the conclusion, but the main problem with this talk is it's very theoretical because it's a giant pain in the ass, right, to implement this. Like nobody wants to write this code, actually. Like either the code with Dyno is like, you know, is pretty black magic, and the other one is like, you don't want to write this kind of low-level code yourself. You just don't want to do that, right? Every time you need a new interface, that's insane. I'm aware of that. So maybe that's something we can do, you know, something about. So perhaps with reflection, we might be able to do something about this. Imagine I define a struct vehicle, and it just represents the interface of a vehicle. So there's just a method in there, it's not implemented. Okay, I'm never gonna do anything with this struct except reflect on it. Go look at what the definitions are in that struct, and then generate some fancy stuff based on that. And then I have something like any vehicle, which is essentially my poly that I had earlier, right? And then I can throw, you know, anything in my vector that contains any vehicle, and it just works. So what I would do basically with reflection is I could, by reflecting on and that's pseudocode based on like the current proposals for reflection and meta classes and all this stuff, which a bunch of people, like including myself, are working on right now. For some of it is going to be in C++20, some of it in C++23. Most of the reflection stuff is aimed for 23. But the idea basically is if I take, I could basically have a type and then use compile time metaprogramming to generate a new type that represents a Vtable for that object, for that interface. So here I reflect on an empty struct, for example, and then I start building up my struct. That empty struct here represents the Vtable I'm going to have. This is all executed at compile time. And so for each method in my interface is this struct vehicle here. So for each method in my interface, I get the signature, I insert a void star, which is going to represent this parameter at the beginning. I create a pointer from that, and I add a public member to my Vtable, which is just a function pointer with that signature. Okay? So I'm just generating a type at compile time, basically one step at a time, based on my interface, which is what represents what my Vtable should look like. And then I just return my Vtable. And I don't return a Vtable with anything in it. What I'm returning here is a meta type, which is a compile time. It's like an object that lives in the compiler that represents basically my struct. Okay? That doesn't live at runtime at all. Not yet. And then a Vtable layout, T here, is an actual type I can use to represent the Vtable associated to a struct that was defined somewhere. So like a struct vehicle, right? And the way I do that is I reflexper on the interface. So reflexper creates this magic compile time object in the compiler that represents a type. With that, that's the object that I get as the input of Vtable layout, okay? And so it creates that object in the compiler. And then I do my Vtable layout calculation at compile time. And then I use something like, I use a keyword, which for now I'm using type name, which basically reifies. It takes this compile time object, which we know represents a type, and it says, hey, Mr. Compiler, please go and generate an actual C++ type from that. And that's what I alias my Vtable layout T2. Okay? So that's all kind of, I expect we're going to get something along those lines. But certainly not exactly that. But I think this is actually pretty cool because now we're just using constexpr programming here. This is normal C++ code with just a few things to basically go to and from the type level to interact with the compiler. But most of it is just normal C++ code. Like it's a normal range-based for loop that runs at compile time and so on. So it's much easier than normal metaprogramming, template metaprogramming. Then you can fill the Vtable. So again, this is all very this is strawman. But imagine you have a, what type you're trying, what type is a model, and you know what your interface is as well. So you generate the Vtable layout, and then you fill the Vtable one member at a time. So for each method in my interface, that should be model actually. For each method in my model, Vtable.idexpr. idexpr is a little bit like type name, or it basically reifies the compile time object into a name that the compiler can use for lookup and do stuff like that, okay? So Vtable.idexpr should read basically as Vtable.whatever the name of the method is. So I'm assigning basically each member of my Vtable with method.address, which is the address of the method inside the model here. So like I said, again, I should be iterating over the methods of the model as opposed to iterating over the interface. I messed up that on the slide. So this code is actually runtime code. And what happens here, like I said, this for constexpr here would do something like do loop unrolling essentially, right? So yeah, this is just, this is kind of a straw man, but I expect we're going to get something reasonably close to that based on discussions within the committee and papers that are currently under review. Yeah, and then you just write the rest basically either by hand or maybe we can generate some more code. So there are ways out of this mess. So that's just one way. Or we could use meta classes, right? Which was actually presented for the first time by Herb last year at this conference. And essentially, we would have, based on the latest paper for meta classes, you would generate your meta class, which is just a constexpr function, in a very similar way as what I just showed in the other slides before. And then you say class angle bracket interface, which is a way of basically applying this meta class to the vehicle. And Vehicle then is basically a class that gets generated on the fly, under the hood by the compiler. So that's kind of a different front end for the functions that I just showed earlier. So we can maybe do it with reflection or with classes, or maybe we can get a custom, or maybe we can get like a custom language level facility. One thing I've been toying around with is if we could somehow integrate this with concepts, it would be really, really, really great, because I have a callable concept already. And all I want to say is I can get any callable, with the right signature, for example, as opposed to creating a new concept or a new interface that basically represents callable, so that I can do type erasure for a stud function, right? My goal is to have exactly one definition of what the concept is, and then be able to generate compile time checks, like the current concepts proposal do, or maybe runtime interfaces. So if I had a way of somehow specifying what methods or what signatures must be part of a concept, then I might be able to generate Vtable from that. Because the current concepts proposal is a little bit difficult in that area, because you basically specify expressions that must be valid, and these expressions are very difficult to map into a Vtable. It's really difficult to say like, oh, because I can say v.accelerate, it means that I have that, like, this thing must return void, first of all. It's not clear at all. It could be anything that is convertible to void, for example. Is it const or not const? And there's all is it ref qualified or not ref qualified? There's all these details which are kind of left out when you're using the normal concept syntax, and you would need these details if you were to generate a Vtable. But anyway, I think it might be possible to bridge the gap in a way that's really nice. That's a nice addition to concepts, and also gives us a lot of benefits on the side. So maybe something on top of concepts. And then perhaps you would use a keyword or a standard library type that is a little bit magic, that generates the interface on top of a concept. So that would basically get us to something like Rust traits in C++, which is really cool. But we can have library customization points, just like we have customization points for coroutines, for example. With coroutines, you have coroutines traits that allow you to define custom, coroutines. We could have different. You could basically have some library level hooks that allow you to specify or to customize the way your storage is implemented or the way your Vtable is implemented. Of course, there would be reasonable defaults, but if you want to go down that road, you could certainly do it with customization points. So what I'm thinking about is some kind of nice language level, maybe add a few simple language level facilities, and then a few library level extension points. And with this, basically getting something along the lines of Rust traits, or basically saner runtime polymorphism for C++. So the goals, of course, are no boilerplate, because what I have today is there's just too much boilerplate, unfortunately. No performance penalty versus hand-coded, handcrafted code. And my goal, I guess my crusade, is really to bring runtime polymorphism without inheritance to the masses. I really want this to happen, because at least in my experience, these gigantic class hierarchies are just a mess. They're just really difficult to work with, and I'm tired of that, because we have better solutions. It's just that they're too hard to implement, so nobody uses that. So I think we can do a lot of progress in that area, and I think it would be a very large service to the C++ community. So as a summary of this talk, basically, if you're just going to walk away with a few things, first of all, inheritance is just one model for runtime polymorphism. There are other options. They might not always make sense, but they exist, right? And it's good to be aware of those. So don't consider not baking the choice of inheritance into a design, upfront. There's many ways of storing polymorphic objects. As always, it's like a space-time trade-off, and it comes with all the complexity that writing performance-sensitive code has, but there are many ways of doing it. And you can Vtable, inline Vtables, but you probably should not do it. And the other thing is type erasure is a big pain, to implement by hand, but it might be possible to simplify it with, some of the features that are in the pipeline for C++ right now. So the library that I presented today is available. Feel free to play. I think it can be useful to bridge some gaps, but it does come with some overhead in the sense that it's a little bit complex to use, right? But it might not be as complex as writing it by hand. I don't know, but it does come with some complexity for sure. And here's a bunch of links. The slides are going to be available. They're actually already online. So you can take a picture right now. It's just a bunch of really useful links, I think, if you're interested in the topic that we talked about today. But this is all going to be posted publicly. And that's pretty much it. Thank you very much.